So far, we have learned how to identify and name several functional groups, which includes some of the ones I'm showing here, alkenes, carboxylic acids, and amines. And they are called functional groups because they have functions, meaning they participate in chemical reactions. In this course, we are going to look at the reactions of several functional groups we have learned so far. But in this video, we are going to look at reactions of only alkenes. First, let's recall what we mean by an alkene. And in the process, I will introduce some important terminology that we will come back to later in the course when we talk about lipids or fats. Okay. So far, we have dealt extensively with the hydrocarbon. Hydrocarbon is just a compound that contains carbons and hydrogens. We've talked about an alkane, which is a hydrocarbon that contains single bonds between the carbons. Here's an example of such an alkane containing 3 carbons. And then we also learned how to draw these as skeletal structures. And that skeletal structure of this compound would look like this. So now we have a term for how we describe these, which is called a saturated. This is a saturated hydrocarbon. Saturated is referring to the amount of hydrogens that are in each carbon, meaning that each carbon contains the maximum number of hydrogens it can hold. So this is saturated. Let's compare that with an alkene, which is going to be an example of an unsaturated hydrocarbon. Saturated carbon. Unsaturated. Okay, so what would this mean? So let's take this first carbon here, and I'm going to now create a double bond with the neighboring carbon, and I'll just leave the last carbon as is for this example. Okay, so if I create a double bond between the first carbon and the second carbon, that means I can only have 2 hydrogens on this first carbon. So if we contrast that with the first carbon in the alkane, we see that this one has 3 hydrogens, whereas this one only has 2. And so for this reason, this carbon does not contain the maximum number of hydrogens that it would otherwise be able to have if this double bond didn't exist. Similarly, the second carbon here contains 2 hydrogens, but in this alkene, it can now only contain 1 hydrogen. Otherwise, it would violate the octet rule. And then our hydrogens out here will be the same. So we can draw this structure as a skeletal structure where we have a double bond between the first and the second carbon. So the terms saturated and unsaturated are going to be very relevant for when we talk about lipids or fats in the next unit. For now, I just want you to recognize the terminology, meaning that when we use the term saturated, if I'm talking about a saturated fat, then you know that that saturated fat will contain carbon-carbon single bonds. But if you have an unsaturated fat, well, it must contain, or it will contain, at least 1 carbon-carbon double bond. So that's what we mean by saturated and unsaturated. Now, let's look at 2 more terms that will be relevant for understanding the structure and the function of lipids in the next unit. And this is going to have to do with isomers. So isomers can be classified into 2 categories. This is what we have learned so far. So I have isomers up here. And then the 2 broad categories that we have discussed is constitutional isomers. Constitutional. And then the other one is stereoisomers. So constitutional isomers, that is going to be what we have talked about so far. I'm going to use the butene, a 4-carbon chain, as an example. So 1, 2, 3, 4, with a double bond between the first and the second carbon. This is called a 1-butene. We are not going to be concerned with naming these in this course. I'm just writing it so that you can see that the compounds I'm going to draw here are actually all different. Okay. All right, so here's a 4-carbon chain. It's an alkene, so it is going to be unsaturated. And it has a double bond between the 1 and the 2. I can draw a constitutional isomer of this, where now I can put that double bond between the second carbon and the third carbon. If I do that, it will look like this. Okay. This is called 2-butene. It is just a constitutional isomer of the first one. Lastly, I can draw something like this, where I still have 4 carbons. So you can notice 1, 2, 3, 4. But now I have a methyl group in that second carbon. So this is going to be called 2-methyl propene. Okay, so the point here is that each one of these is a constitutional isomer because they all contain 4 different carbons. they contain the same amount of hydrogens, but the difference between the three is that they differ in the way the atoms are bonded to each other, meaning the double bond is in between the 1 and the 2 in this one. In this other example, is between the 2 and the 3. Okay, but the number of carbons and hydrogens is the same between all of them. This is what we mean by constitutional. Now let's contrast that with stereoisomers. So now I'm going to take this 2-butene molecule here, this 2-butene, and I'm going to draw it over on this side, but I'm going to draw it just a little bit differently to emphasize the conformations that we're going to be talking about. So I'm just going to go ahead and draw my double bond in the plane of my paper. I'm going to draw it horizontal. So that is this double bond here. And I'm going to draw each methyl group on either side of my double bond. I can draw them both facing the same side of my double bond, or if I have a double bond, I can put one methyl group on top and the other methyl group on the bottom. Okay, so you have the option of drawing it in these two different ways. And these are actually two molecules that are going to have different properties. Okay, let me just draw that a little bit more straight. So when the carbon-containing group, so notice I'm not focused on the hydrogens on either side of here. Locate your carbon-containing groups. If both of them are facing the same side about the double bond, meaning you first locate your double bond and look at whether they are both in the same side. That is going to be what we call a cis configuration. If the groups, the carbon-containing groups, are on opposite sides, as I've shown it down here, this is going to be trans. So what this means is that I could also draw this cis configuration like this. This is still cis because the carbon-containing groups are on the same side relative to your double bond. This means I could also draw my trans configuration or in a different manner like this. But again, this is still trans because my carbon-containing groups are on opposite sides of that double bond. So the double bond is going to be your reference here as to whether something is cis and something is trans. It turns out that most naturally occurring fatty acid, which is a type of lipid that we consume, is going to exist in the cis configuration. So it's going to exist like this or like this, right? Both of them are cis. However, when we process unsaturated fats, and we do this in order to improve their shelf life, we use a process that's called partial hydrogenation. So we use this process. Let me grab a different color. We're going to use a process that's called partial hydrogenation. And sometimes this process can produce fats that are in the trans configuration, this configuration, which is not a fat that we can process easily like we do with the cis fats, which are naturally occurring. So what this means is that sometimes these trans fats can be in our foods, which our bodies are unable to process properly. Okay, so I'm bringing this up because, yes, this will be relevant for when we talk about lipids, but also this reaction, hydrogenation reaction, is going to be the first reaction we are going to talk about. So let's go ahead and look at what we mean by hydrogenation of alkenes. Okay, so this is going to be one of the two reactions that we are going to look at. So as you've noticed so far, how we name things and the names that we use in organic chemistry, they are made with a purpose, meaning that they can provide information as to what structure we're talking about or what process we're talking about. Here we're talking about hydrogenation. So let's look at this word. You can see that we have the word hydrogen in there. So this is telling you that this is going to be the addition of hydrogen. Addition of hydrogen. And recall that hydrogen does exist as a diatomic molecule, so that's going to be H2. So you have two hydrogen atoms in there. As we go through these reactions, I will introduce terminology that we use to describe the types of reactions that occur, even outside the context of alkenes. So one of those terms is going to be addition. So we have what are called addition reactions. Hydrogenation is an example of an addition reaction. And the reason it's an addition reaction is because we're going to add hydrogen across the double bond of an alkene. So let's see what that will look like. So right now I have a carbon double bonded to a carbon. Again, this is necessary in order for me to have an alkene. And then these carbons can be bound to anything else. It doesn't matter. I'm not going to write carbons or hydrogens in any of those bonds because it doesn't matter what's there. But just recognize that at each one of these ends, there's either a carbon, some carbon group or a hydrogen. Okay. So this is a representation of some alkene. And again, the emphasis here is just on that double bond between the two carbons. Now, I'm going to react that with hydrogen. I'm going to draw it like this to show its bond, because in a reaction, basically what a reaction is the making and breaking of bonds. All right, so these two are going to react together. How will that happen? Well, in order for things to react, I'm going to have to break bonds. First, I'm going to break one of these double bonds here. So let's say I break the lower bond, it doesn't matter. Okay? So when I do that, I'm going to break those two, and I'm going to get a compound on this side, where now I just have one bond between the two carbons, and then whatever was bonded to these carbons remains. Okay? But notice what happened when I broke that bond. Each carbon here does not satisfy the octet rule. So now it has room to make new bonds. So that means that I want to break this bond here. So this bond here is breaking, and this bond, one of the double bonds there is going to break. So if I break the hydrogen bonds, that means one of the hydrogens can now bond to one of the carbons to satisfy that octet rule. And then the other hydrogen can bond to the other carbon. And this is what we mean by addition of hydrogen, because if you look at this region here, let me do that in a different color. If you look at this region here, this is two H's. We have basically added hydrogen. Okay, so notice what we have made on the right-hand side. We have made an alkane. So hydrogenation of alkenes allow you to go from an alkene to an alkane. And this is how we can convert different compounds. Most of the reactions we will talk about in this course will require what we call a catalyst. This is just a compound that increases the rate or the speed of your reaction, but it's not going to be consumed in the process. For now, all you need to know about a catalyst is that it increases the rate of your reaction, and we will talk much more about this when we talk about metabolism. For now, the compound that you would see being used as a catalyst for this reaction is called palladium, and you can draw that, or you can write that either above or below your arrow. So I'm just going to write it above. Sometimes you'll see it below. All right. So this is the basic anatomy of your hydrogenation reaction. So let's go ahead and look at some examples. Okay, draw the product of the reaction when each alkene, so this is my starting material, is treated with excess hydrogen. So this is going to be my other reactant in the presence of a palladium catalyst. Okay, so let's look at our first molecule here. I'm going to draw my arrow like this, basically just to show that I have a reaction happening. And this is to save a little bit of space. I'm going to draw H2, which is my reactant here. And then I'm going to draw PD below my arrow just to show that I do have a catalyst present in this reaction. Okay, they have told me I have excess hydrogen. The reason they have said this is just because you need to have enough hydrogens around if you are going to have multiple double bonds. So you see here I have multiple double bonds. Here I also have multiple. And you just need enough hydrogen around in order to make sure that all of your double bonds you have enough hydrogens to add to all of your double bonds. Okay, so let's look at the first molecule. All right, so the first thing I'm going to do is break the carbon-carbon double bond so I can open up room for my hydrogens to bond to that carbon. Otherwise, I would be violating the octet rule. So I'm going to go ahead and break that bond. So now there's only a single bond between the two carbons, and I'm going to keep all of the groups that are bound to those carbons. Okay, so now I have room to add my H's from the hydrogen. So I'm going to write those in blue, and I'll just put an H here, then another H here. And again, these are coming from my H2 reactant, which I will also just write in blue to keep it consistent. So that is what's happening here. I have added hydrogen across my double bonds. We tend to speak about it this way. Okay, let's look at the next molecule. I'm going to go ahead and react it in the same way. I'm going to use that little arrow. Palladium is my catalyst, and then I will use this blue to show H2. Okay, so the first thing I need to do is break my double bonds. I'm going to notice I have one double bond here and another double bond here. but that's fine. I have excess hydrogen, so I'll have enough hydrogen to add to all of those bonds. Okay, so the first step is to draw your molecule. All right, and now I have broken each double bond. But what I have also done is added hydrogen to each side. So I broke this bond here, and then I added a hydrogen there, a hydrogen here. I broke this bond, added a hydrogen there, and a hydrogen here to make sure it's satisfied. But recall that in skeletal structures, we do not draw hydrogens in. So really, it's just going to look like your double bond disappears, which is essentially what happens. I'm going to draw this a little bit better. So at this point, you recognize that you had to break your double bonds, and then you replaced those with hydrogens, and you can't see them in a skeletal structure, so your double bonds disappear. Let's do the same thing here. We're going to have palladium, then we also have H2, but again, since we're going to draw skeletal structures, we won't be able to see them. So here, I'm going to break every single double bond. I have one here, another one there, and another one here. And then I'm going to place hydrogens on either side of those double bonds. One here, and then another one here. Okay. So now all that is left is for me to draw my molecule after adding hydrogens across all of those double bonds. So that just means I'm going to draw an alkane. This alkane contains 12 carbons and then an OH group at the very end, or a hydroxyl group. So I'm going to go ahead and draw them. 1, 2, 3, 4, 5, 6. Let's correct that. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then at that very last carbon, I have an OH. And then there are going to be methyl groups along this chain. And now all of my double bonds have disappeared because I have added hydrogens on both sides of that double bond and broken the double bond. Okay? And that is all there is to hydrogenation of alkenes. It just means you're going to break that double bond and you're going to add hydrogens to the 2 carbons that were involved in that double bond.